guys, this is Professor Janacek, and I want to go over some more examples where we find equations of planes. Here we have example 4. Let's find an equation of the plane through the point 0, 2, negative 2, and parallel, to another plane. This plane is Q, which is described by 2x plus y minus z is equal to 1. All right, so just like before, I'm going to go ahead and label this point x naught, y naught, and z naught. And parallel means that it has to have the same normal vector. It's one way of considering two planes are parallel. Well, let's see. In this case, my normal vector, remember this is ax plus by plus z is equal to some d value. And so that means our normal vector is 2, 1, negative 1. So that's exactly what we want to use. Well, let me write that here. Don't need it there anymore. And so now we're ready to go. How do we find the equation of a plane? Well, again, this is A, B, and C. So we'll have 2 times x minus 0 plus 1 times y minus 2 minus 1 times z minus negative 2 is equal to 0. So that gives us 2x plus y minus 2 minus z. Ooh, watch all this subtraction and these negatives. We actually end up with negative 2 equal to 0. So we have 2x plus y minus z is equal to 4. And there we go. This one is through our point P and parallel to the plane Q. All right, one more example. Let's find an equation of a line of intersection, a line of intersection through, now we're given two planes. Plane Q is x plus 2y minus z equal to 1, and plane R is x plus y plus z is equal to 1. Oh, all right, and I'm looking for a line of intersection. Now I have to remember how to find a line, not a plane. It's a little different. So let's see here. First off, let's jot down our normal vectors. The normal vector for Q is 1, 2, negative 1. And for R, we get 1, 1, 1. Now, I notice that these are not, one is not the scalar multiple of the other. So that tells us Q and R are not parallel. That's important because if they were parallel, then they wouldn't have a point of intersection. But they're not parallel, so they must intersect somewhere. Now, I've got to find this whole line of intersection, but to start with, let's figure out what a point of intersection is. So let me just kind of take this back to just the xy plane. See if I can find which point where they intersect in the xy plane. Well, first off, in the xy plane, I know that z is equal to 0, which means I can rewrite these equations. X plus 2y is equal to 1, and x plus y is equal to 1. And then we can solve this. You could use substitution or elimination or even matrices or something like that. Let's see, we would end up with, take a moment, make sure you know how to do this. See, I think I end up with x is equal to 1, and y is equal to 0. All right, so this was in the xy plane. It's simply a point, but this is where they intersect. Thus, this point 1, 0, and remember the z value is also 0. It's a three-dimensional point. This is a point of intersection. So it's a point on the line that we're looking for. Okay, so I have a point. I now just need a vector in the correct direction. All right, well, let's see. I'm going to make a statement here and see if you agree. Since these two normal vectors that we had, in Q crossed with in R, since the cross product is parallel to the line of intersection. Now I'm going to use this idea, but let me first just make sure everyone agrees with this. So, in Q cross in R is parallel to the line of intersection. Let's just make sure we agree with that. Let's think about what we have here. So suppose we have a line of intersection. Oh, let's see, how do I want to do this? Let me do it this way. Oh, that's terrible. I'll just go back to that. And something like that. Okay, so there are two planes. Suppose this is our two planes. And of course we can see where they intersect, but let's also take a look at the normal vector. So if I have this normal vector is here and this normal vector is there. All right, so let me just label these so you know what I'm talking about. Let me say that, I want this one to be in Q and this one in R. So this is Q and this is R. And these are the normal vectors. Just identify that. All right, now if you think about what's going on here, if you were to take the cross product of these two normal vectors, remember the right-hand rule, cross product, where would that be going? Well, it turns out it's going to be parallel to that. It's going to be coming out kind of towards us, but it should end up being parallel to hopefully you see parallel to our line of intersection. That's what I'm looking for, something more along those lines. So again, think about the cross product and remember the right-hand rule, and out in three-dimensional space, that should be parallel to our line of intersection. Okay, whew, I hope that's clear. Now, we can make that statement. Since this is true, then of course, all I need to do is find the cross product. Again, make sure you remember how to do this. Take your time with it. Let's see, we end up with, again, take your time with this. I think our first term is, first component is 3. Let's see. And then a -2. And then a -1. Yeah, that works. Okay, again, make sure you understand how to do that. Take your time with it. Okay, so now we want let me start by, now what we're going to do is go back and kind of find the equation, again, of the line. That's through the point, I'll call it P naught, is 1, 0, 0, and in the direction of this vector 3, negative 2, negative 1. So we'll call this R naught. It's the vector in going to point P, so that would be 1, 0, 0. Again, it's a vector now, whereas this was a point. And we'll let R naught, not R naught, V be the vector 3, negative 2, negative 1. Don't forget how to find the equation of a line. It's R equal to R naught plus VT. All right, so that gives us R is equal to 1 plus 3t for the first component, negative 2t for the second component, and negative t for the third component. And there we go. There is our line of intersection. Whew, wasn't that exciting? Enjoy!